If there is anyone new to our presentations, welcome to the Science Circle and our weekly presentations on lots of different subjects. And so I'd like to, I was supposed to present this a few weeks ago, and my computer connection was down because somebody had bitten into the cable outside, blah, blah, blah. But now it's up, and so I get a second chance at presenting this. So, welcome to our presentation on Saturdays, and let's get started. Okay, so seasons in the solar system, what could that possibly mean? Well, first of all, as I mentioned, oh, by the way, if you are new, or even if you're not, I love chat. I can do chat at the same time. In other words, I know what I'm going to say, more or less. I've got the slides and made them. So I like to do chat at the same time. So I say hi to people. You can ask questions, answer questions, comment, get off topic, whatever, as long as it's all civil. And so this is what I call a relevant non sequitur. That is, why would I possibly, chat, mumble, okay. So why would I possibly come up with a topic called seasons in the solar system? Well, it's because something, in other words, there's always something that starts it. I like to do presentations on problems because it kind of starts with a spark. Something starts it, and then it kind of goes like, what if? What if this? Imagination, like it was mentioned earlier. So it kind of ignites a train of thoughts, results in basically going out and researching, extending our knowledge. Okay. So anyway, I was thinking about the winter solstice in December. And then I realized, of course, that it's not the winter solstice for everybody. It just happens to be to every thing, turn, turn, turn. There is a season. Anyone remember that song from long ago? You have to be older. Okay. Yeah. Okay, so winter solstice back in December, the birds, perfect. And then realized that it wasn't that worldwide. In other words, for people in Australia, for people on the equator, it's not the winter solstice. So I was thinking that Mars, too, has changes because you get these big dust storms, and the poles have dry ice caps on them and stuff. And so I was going, well, what about other bodies in the solar system? So I kind of researched and then imagined, as mentioned, now I'm sharing it with you, so that then you can share in chat or with other people. You can share what you think about this topic. That's kind of how science works. Okay, but as I was telling Sis and others earlier, is that in order to do this properly, science that is, oh, now I see dots on just about everybody but D, if anyone wants to help out with that. Okay, so the idea is you've got to define your term. What is a season? And so people were mentioning this, and so you got to, in other words, if you're going to be doing this stuff, you need to describe exactly what you mean by terms that can be ambiguous. That way we can limit or expand our scope, because my definition of season is a bit more, well, you have a dot. There's a dot. I look under conversations, and if I see dots there, then presumably everybody can hear me. Yeah. Okay, and then if I see my dot having green, then I know people can hear me too. Presumably. Yeah, it's okay. Okay, so anyway, let me keep moving on this. So season can mean lots of things. It can mean, if you're in the middle latitudes on Earth, it can mean that there are 4 divisions of the year. Yes. Which actually I did, I did that to somebody the other day. They were talking about Morse code, and so I sent them a chat in Morse code. Yeah, Rosemary also in time. Okay, so 4 divisions of the Earth marked by daylight hours and weather patterns and stuff like that. That could be one way to look at seasons. That's more the conventional way if you happen to be living in the middle latitudes, either north or south hemisphere. Or you can expand that to mean a time that's characterized by certain features, migrating, mating season, flu season, or as somebody put, sports season. Okay, or a sequence of events. Now that's actually more like sports, TV. There doesn't have to be a particular features. It just happens to be, football season or soccer season or something runs from blah, 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 that sort of thing. Okay, then it's time travel. Okay, well, I always love Siz's wit here. Or colloquial, that is like somebody mentioned spice, so adding spice to food is season, or spicing or seasoning wood, blah, blah. Okay, let's go on to our topic. It's just that I wanted to explain how I got to the topic. Okay, so our solar system, if I wanted to find it, is full of all kinds of stuff. There's a star. A lot of solar systems have more than one star. There are almost stars, like Jupiter would be a kind of a star if it were about 10 times more massive. Yeah, Ty-Curry is good. Okay, so in any case, there's planets and stars and moons and all kinds of other stuff. And so if you look at that other stuff, if you zoom in, you got comets, you got Pluto and Charon and all kinds of stuff. Do you know there's actually that Maki one in the, yeah, I was looking for one that showed the entire solar system. And if you actually look at Eris, E-R-I-S, it's over to the right of Pluto. It's actually bigger than Pluto. It's in the Kuiper Belt area, and it's slightly bigger than Pluto. And then you've got the Oort cloud, which is so far out that the Voyager spacecraft, even though they're, and the other ones won't even reach them for 300 years. Yeah. Okay, thank you. Okay, I always like to get nice. So in my case, that's the solar system, and seasons are kind of a cycle. In other words, not a one-time event, but a cycle of changes and their consequences. So you've got winter and stuff. Okay, so let's move on. I'm starting from the inner part of the solar system. So does the sun have seasons? Well, in my definition, it does. Because, and like you said, I'm kind of doing a you can't hear anything too. Check for dots. Emmelock, okay. So help people out if they don't have dots. Well, either relog or go up to in my case, the upper right and check to make sure things are clicked, and then click them, unclick them, all that stuff. And also Zoom, like what Mike says, if you go to Zoom, you could often hear even if you can't hear in Second Life because you're hearing what he's hearing, okay? So now the sun, let's take a look. Does the sun have seasons? Well, the sun magnetic field happens to flip every 11 years. And so you have the consequence of that is, by the way, does anyone know how often the magnetic field of the Earth flips? This is my, from a non sequitur standpoint, this is my, okay, Max says no. Okay, good. Good question. Actually, it's about 50 million years, I think, okay? Because if you look, the way you can tell is with seafloor spreading, is that you can tell with the magnetation, the magnetic orientation of the seafloor. If you look at the seafloor, it looks almost like stripes radiating out from the mid ridge of the oceanic mid ridge, that sort of thing. 14,000, is it? Okay. In any case, there's stripes radiating out, and in one case, the magnetic field is in one direction, and then in the other direction. And so it happens on Earth. By the way, does anyone see that? Did anyone see that the magnetic pole is moving quickly right now on Earth? In other words, it's there's a change in the magnetic pole. It had been pretty much through the 1800s, 1900s in about the same. Oh yeah, absolutely. So in other words, the magnetic pole reflects what's going on in the core. Oh, okay. So Sis has got a good answer there. As often as and as infrequently as. There's where the 50 million one comes up in my brain. Okay. So right now, yeah, the polar, absolutely. So the compass will point differently. In fact, they're having to change what's called the world whatever WWC, I think, and I don't mean wrestling. I mean in terms of navigation, etc. Magnetic poles, but look it up. They're really changing quickly over the last 20 years. There's more of a change in the poles in the last 20 years than there were in like 200 years almost. Could be. Okay. In other words, it's moving over toward Russia, Scandinavia, that area. Okay, government's doing it. Yeah, secret. Okay, I got to keep moving. Okay, so sunspot circles. So the sun's magnetic field flips every 11 years. And what we see then is these magnetic loops that send out massive bursts of energy. If you look at it head on, it looks like a sunspot. If you look at it on the side, these big loops of magnetic loops of material are solar prominence. And so the consequence on Earth is that it can interfere, it can get past the Van Allen belt, some of it can, and then damage electronics and power grids, and that's what creates the northern and southern lights, because the pole then loops into the magnetic north and magnetic south. That's what you have there. So essentially what I'm saying here is that the sun has a season of every 11 years. Now, yeah, I've seen them when I was up in above the Arctic Circle in Norway and in Alaska, but because of we're at the, right now, if you look at the bottom right of this slide, you'll see that 2024, we're at the solar maximum. In other words, the number of solar sunspots and stuff is at its maximum for this 11-year cycle. Yeah, and they don't stay like that. They move constantly, different colors, and it's a pretty interesting display. And so the sunspot cycle is predictable, at least in terms of hundreds of years. Yeah, very dynamic, very dynamic. Okay, and you can see in this slide over on the right there, you can see this is what's called cycle 25 that started back when we first knew about this, back in 1600, somewhere that time period, 1500s, I forget when, but this is cycle 25 that we're in right now. And so you can see that over 400 years that there have been ups and downs in the number of solar sunspots. So there can be as many as 250 sunspots during that cycle, 25, in that time period, or there could be in what was called the Maunder minimum, which was back in the time period of what was called the Little Ice Age, which right now people are saying those are coincidence. It didn't say one caused the other, but it says it's a coincidence, is that there were almost no sunspots in some years where there was no sunspots at all. Okay. So in other words, seasons on the sun create changes here and consequences here on Earth. Okay. So now let's take a look then at Mercury. So does Mercury. Okay, well, as I've mentioned, seasons denote change. So what creates change for the solar system? Meanwhile, back at the Bates Hotel. And then let's see, the shower scene. Okay, let's see. So change tends to come from energy. Energy primarily comes from the sun. But you could also have seasons due to the motion of the object, the gravity, its radioactivity. In this case, Mercury has no tilt. Okay, what is the tilt? This is my time when I make sure all of you guys aren't out getting coffee or looking at the nice morning or something, is how tilted is the Earth from the plane of the solar system? This is a relatively simple. Yeah, there we go. Okay, rounded off. Okay, 23.5 degrees. So Mercury does not have that tilt. It's more or less no axial tilt, but it does have a couple things that the Earth does not. And this is really interesting. This is, well, actually 23.5, but, and it can range from around 21 to 24, and I will talk about that in a second, so Mercury has a, thanks, Tag, the mathematician comes out. But, yeah, from the, exactly. Okay, now, yeah, in other words, the rotation, think of the moon. Okay, the moon is tidally locked to the Earth. So its day technically is the same as its month. It always shows the same side to the Earth, but Mercury's big. And so it's not tidally locked to the sun, but there is a, says, and there is a resonance. There's a 3-2 resonance, which I'll show you in a minute and what the consequences of that. Yeah, it's very dense. In other words, Pluto and Mercury are about the same size, or is it Pluto? But Mercury is like 4 times as dense as Pluto. Something that, or Titan, one of those two. I think Titan is the one that's Mercury's 4 times. Mercury. It's very, very dense. They found out that its core, because we had a spacecraft go near there. Okay, I got to keep moving. Okay, so anyway, the variation because of the elliptical orbit can be in other words, it can get as much as 1.5 times the distance and the radiation. And also, of course, since there's no atmosphere, you've got 450 degrees Celsius on one side, minus 108 on the other side, and variation due to the latitude. But look at this one. This is a really cool thing that I found out about Mercury. Because, and you'd have to do a kind of a model. Well, actually, Emmelock, I think Mercury is more dense than Earth, but you want to check. They're all rocky, third rock from the sun thing. But you might want to check on that. But they're both, Earth is very dense, partly due to the fact that it captured a lot of material from the proto-moon. At least that's the theory. And then Mercury also is very dense. So virtually everything that that didn't collect there has been boiled off over the years. Okay, so watch this one. Okay, Mercury's day is a result of this 3-2 resonance. And you can see it right there. In other words, 176 days, or 176 Earth days for the day, but the orbit's in 88 days. That's a 2-to-1 resonance. And then the day rotation, 176 to 58.5 days, that's a 3-to-1 resonance. And so what results is, the Earth is actually, okay, good, thanks, Sis. Iron core takes up a lot of its volume. Good point, Mike. Okay, so what this results is, if you were either on the 0 or 180 longitude, look at the diagram down at the bottom. I found this really strange. So the seasons are different depending on what longitude you are, not necessarily what latitude. In other words, the sun, there's one sunrise and one sunset daily if you're on 0 and 180, and then the sun hangs around up at the apex, goes slightly retrograde, comes back, so it spends a lot of time up there near the apex. And then down at, if you're on the 90 or 270 longitude, there are actually 3 sunrises and sunsets every day. In other words, it doesn't spend a lot of time up on the apex. It comes down, dips down below the horizon, comes back up, dips down below the horizon pretty quickly. So actually, the longitudes 0 and 180 receive 2.5 times the, ironically, Mercury would be buoyant in Mercury. Yeah, because Mercury is very dense. That's very funny. That's like Saturn, them saying if Saturn floated in the ocean on Earth, it actually has a, Saturn is less dense than water. But I don't know of any swimming pool that you could put Saturn in. Okay, so moving on. So Mercury has a very odd seasons depending on longitude, not necessarily on latitude, because of this weird 3-2 resonance. I bet you know, but did anyone know that? I had no idea. Okay, so, yeah. Okay, I didn't know it. Okay, so I thought it was pretty bizarre. Okay, so now, this is, of course, people, when they go, what does it look like on Mercury? Here's an example. By the way, the sun is a white-looking star. We tend to think of it as yellow because we see it as yellow in the Earth's atmosphere. And also, if you look at the spectrum compared to other stars, it's kind of a G2 something star, so it's kind of in the yellow range. But if you actually are out in space, like at the International Space Station, the sun is white looking. It puts off white light. In other words, lots of all of the frequencies. Yeah, G2V variable, I guess. Okay. So this is what somebody's idea of what Mercury looks like with the sun near there. Of course, they're probably going to make it look like the moon because it's more like the moon than it does like Earth. Okay, so how about Venus? So on Venus, even though it's the size of the Earth, they're almost like twins, it's much closer to the sun. And so the atmosphere, it's got an atmosphere like Earth, and so the atmosphere does a lot of distribution of heat and buffering of the, okay, night with Venus. Okay. So large solar system bodies tend to have the gravity that retains its atmosphere. So Venus is a lot larger than Mercury, and it retains its atmosphere. It has significant atmosphere. And then they tend to moderate changes and distribute temperatures so you don't have these wild, 450 degrees Celsius on one side and minus 180 on the other, that sort of thing. But it has almost no tilt. It has a circular orbit, and its day-night cycle is about the same as its orbit. But because it's different, actually the sun, because one's longer than the other, the sun rises in the west and sets in the east, or at least, that's what it appears on Venus. So it's opposite of Earth. And the biggest thing is that the atmosphere is really thick. So the atmosphere prevents seasonal changes. So if you were on Venus, it would just be hot, 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 no matter where you are, anytime and day. Okay, so what does it look like on Venus? Anybody? Has anybody seen? Has anyone seen Venus? I mean, not you, but has any? Yeah, it looks hot. Okay, so has any? Yeah, there you go. Perfect. Brandy. Orange. Yeah, exactly. Okay, so there you go. This is Venera 13, which landed there in 1976, And boy, that doesn't look very hospitable. It's 900 degrees, 50 or no, 90, 50 atmosphere, something like that. Just really, really not very hospitable. The spacecraft actually was able to take pictures for 2 hours, and then it something melted. 900 degrees Fahrenheit, which whatever that translates to centigrade, it's still above the melting point of lead. So not very nice. And this is pretty much what a lot of the place looks like on Venus. So moving on, let's take a look at Earth. Earth, we know, has seasons, but if you actually say, okay, what's the seasons on Earth? It depends a lot on where you are and then what is going on. So because there is a tilt relative to the orbital plane, is that it has a moderate tilt. That's not nearly as much tilt as some of the other bodies in the solar system. A nearly circular orbit and a short day. In other words, it's not 176 or 60 Earth days. It's one Earth day. Ha ha ha. Okay, which is moderately rapid. Okay, that's why the Americas is a diamond. Okay, yes, indeed. Okay, so the days are short, which means that the night and day temperatures minimize to less than 50 Celsius. In other words, if you look at, depending on where you are, particularly in the desert, it might be 50 Celsius at night or close to 100 Celsius at night. There's not 50 Celsius, sorry. That's 100 centigrade. And then down there freezing at no, Venus has what looks or appears to be a retrograde day. That is, on the surface of Venus, the sun sets or rises in the west and sets in the east because of the difference between its day and the orbit, which is different than on Earth, like in Oz. Is that in Oz? It doesn't? Okay. Yeah, okay. So anyway, on the Earth, the atmosphere then retains heat, so it lessens temperature variations at night. The axial tilt then changes the angle, and then thus the energy of the solar rays which arrive. So let me tell you a little bit more about it. So anyway, on Earth, the effect of the tilt, if you look at the same amount of sunlight and then the amount of space which absorbs that, you'll see that in the mid-latitudes, the difference can be, depending on whether you're summer or winter, it can be up to 3 times different for mid-latitudes, but as much as 6 or 7 times as much in summer versus winter as far as the amount of radiation that hits a square meter or of surface. And so the summer and winter effects for northern latitudes and southern latitudes, or poles, let me put it that way, are much greater, which is part of the reason why we've got such, during climate change, why we've got so big a changes going on. But that's a whole lecture in itself. Okay, so there are other effects as far as altitude, water, that sort of thing. So temperature is affected by many factors. It could be the tilt, but also when we say climate, what we're talking about is long-term weather patterns, global, regional, not what is the weather today, tomorrow, locally. Elevation, so we all learned back in, if you took science back in school, if you go high up in the mountain, it's as if you're going further in altitude. So you can have a polar region pretty much at the top of a mountain, the same as you would going high latitude. Yes, and hang on a second, Syzygy. I've got other slides on that one. You're right. In other words, I'm just kind of moving from day-night to effects with seasons. But if you go on if you're in the equator, there are also wet, dry seasons. In other words, there aren't the 4 seasons that you normally have, but because of the way that the yes, Briony, I will mention that here in a second too. So the idea is that if water is available, like let's say the Amazon, where you've got the Atlantic and the Pacific there, and India and other places, you'll get these storm conditions, monsoons, hurricanes, typhoons, tornadoes, that sort of thing in as far as seasons goes. So like the Amazon has basically a wet and dry season. Same thing with South Asia. So here's a couple of questions. Why does it get colder or hotter after the solstices? In other words, the days are getting longer right now than they were in December, so how come we are getting colder in January? So the idea is that if you're talking globally, that essentially it takes a while. It's kind of inertia, so to speak. It takes a while to warm or cool, particularly bodies of water and the atmosphere. Because of the properties of water, it takes quite a while to cool it or to warm the oceans. And then, okay, so how do different places on Earth experience it? Well, in the tropical, like I said, it could be hot, humid, or dry seasons, cold currents, wet seasons, that sort of thing. Mid-latitudes, you've got kind of hot and cold in between. Poles, night and day, more insulated in the south, which is why we've got these polar vortexes coming down from the north. Like I said, this can easily be, well, it is a tilted position, impact on biodiversity. Like I said, this whole thing could easily be a whole presentation in itself, which it might be. Okay, so long-term effects, because I got to keep moving because I've got the solar system, the rest of the solar system. Okay, so long-term effects, there are changes to the orbital tilt ranging from 22 to 24 degrees over a 41,000 year period. The Earth wobbles like a tilt over a certain period of time, so the North Star actually changes from, like, say, back from when the Egyptian days. It's in a different place now. The last greatest tilt, in other words, the 24.5 was actually at the beginning of the Holocene epoch, which marked the end of the last ice age, about 10,700 years ago, which is beginning agriculture, et cetera, et cetera. And then what the currently decreasing tilt, right now it's decreasing, which it basically means that it'll be milder seasons and less insulation than in summer. In other words, you won't notice it quite so bad. Okay. Well, it just, in the tropics, you don't see a lot of the changes. Oh, why does the tilt change? Oh, because it does. It's S-tis. It has to do with, yeah, okay, there you go. Okay, it also has to do with, frankly, we get little perturbations. In other words, like Mercury has this 3-to-2 resonance. Well, Jupiter and Saturn all have resonances, and then they also have enough gravity to control things over long periods of time. Rotating top. I mean, there's lots and lots of different, due to other planets, sun, etc. So there's lots of different reasons for this over a long period of time. Let me move beyond here. So orbit shape, eccentricity, so lots of interactions. Absolutely, very complicated. However, we know what some of these are, so we can actually predict. So over 100-year cycle, it will actually go from almost a circular orbit to a slightly elliptic one due to the gravity effect of Jupiter and Saturn. And actually that anytime you get something that's not circular, just like Mercury, it actually accentuates the seasonal changes. And so as I think it was or somebody mentioned, sorry if I don't remember exactly who is that the summer is 4.66 days longer than the winter in the north than in the south because of some of this stuff going on here. Eccentricity, in other words, when the north and south. Okay, and then really long changes is really long-term effects is like I think Sis mentioned with the precession, rotation, orbital plane, and you get these temperature spikes. This is over a very long period of time, where you've got cycles of 100,000 years corresponding to the ice ages, et cetera, et cetera, et cetera. Yeah, actually, the Earth kind of looks like a pear. If you actually look at it. In other words, it's like 50 miles more in diameter around the oblate spheroid. Yeah. Okay, so now if you go back even further to, Earth-Moon system, also changes a bit. Okay, now if you go back even further to hundreds of millions of years, you'll see that there's been vast changes in the global temperature, and we're now actually in what's called an interstitial period. In other words, we're still in an ice age, but we're in the warmer part of the ice age compared to, like, say, when it was dinosaur days or the frozen Earth, snowball Earth, and all that good stuff like that. Okay, let me move on to the next planet, which would be Sun. Okay, if you go back billions of years, now you're talking about even more changes, because the earlier Sun, if you go back like 300 million years ago, or 300 million years old, in other words, 4.5 billion years old ago, then you're talking about lots and lots of sun. In other words, the sun is actually getting kind of milder than it was long, long ago. There are a lot more. We had joy, we had fun. There were seasons in the sun. Okay, I know that one. I'm old enough, but I don't remember who did that one. Yeah. Okay. Okay. How about the moon? Does the moon have seasons? By my definition. Yeah. Okay. Artistic license. Well, yeah, Illing, not so much, because even though it's the size of a small planet and it's the same distance from the sun as the Earth, of course, it doesn't have a atmosphere. There's what's called an exosphere, which is very, 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 very thin. It's kind of like what the atmosphere is up by the International Space Station, which is kind of a little bit of helium, a little bit of hydrogen, a little bit of stuff like that. So it doesn't. So there are bigger changes in the day and night temperatures, depending on sunlight, because there's no atmosphere. But the day and year are essentially the same, which is the length of the month. You know, it's 28.5 Earth days long, and there's no magnetic field, so the solar winds basically increase with the 11-year sunspot cycle. And so, yeah, not seasons as we know, but there are some changes. Okay, and then, of course, here's a view of what it looks like on the moon, at least the last time we were there. Okay, so now, Mars. Does Mars have any changes? Yeah, doing the moonwalk. Okay, yeah, Mars does. Mars, first of all, Mars is tilted coincidentally at essentially the same tilt as the Earth. And so it also has the, except for Pluto, the eccentricity of the orbit, in other words, how elliptical it is more than any other planet except for Mercury, and Pluto doesn't count anymore. And then, so the combined effects is essentially you've got a summer and winter accentuated by its thin atmosphere. And so you end up getting these dust storms, and on the poles of Mars, you've got polar ice caps which grow and recede, which are made of dry ice. So you can see pictures of it, especially down on the bottom right. You can see in the North Pole that you've got a pronounced North Pole during the winter, and that basically it almost disappears in the summer in the North Pole, and vice versa in the South Pole. That sort of thing. Okay, how about Jupiter? Before I turn to Jupiter, I have 15 minutes. Yeah, you would need a lot of sunblock. Now on TAG, is that I don't know how much UV you would need, but you certainly get all the radiation. So I would definitely wear sunblock, I guess, on Mars, except for the fact that 250. Yeah, except for the fact that you'd already be in a spacesuit because you can't wander around in your bathing suit on Mars for long. For one, it's cold. I think it gets 50 degrees Fahrenheit or 10 degrees Celsius at the max in the equator. Okay, so here's some pictures of, wear a hat with a brim. Okay, so Brittany says Jupiter. She's brave enough to say that Jupiter does not have seasons, and actually you're right. But we are not there yet. Okay, so here's some pictures of Mars. Now, to me, this could be a lot of places on the Earth. Look at those sedimentary layers over on a super wide ring. Okay, so look at the sedimentary layers that look almost windswept over on the left. Then you've got this rock minefield there on the bottom right, and it looks like a lot of places on Earth. Okay, so now Jupiter. There's several things going on with Jupiter. One is that it has almost no axial tilt. It has a slightly elliptical orbit, but it's cold. And the biggest thing about Jupiter is those bands are created because there's storms. Notice that they're mostly mid-latitude storms, but because the rotation rate is 10 Earth hours. In other words, you got this huge planet where the diameter is 10 times, gas giant, is that the diameter of Jupiter is 10 times the Earth, and yet it goes around in 10 hours. So you've got 1,000-mile-an-hour winds on this thing and all the time. And so what that does is essentially it creates these bands. Very breezy, but the combination of extreme cold, rapid rotation means that there's no seasonal changes because whatever heats up or cools down is going to be on the other side of the planet quickly. So it basically distributes that heat. And then so Jupiter's moons have kind of day-night cycles, but no seasons either. So now you can't show a picture of the surface, tie them down very securely, except for the fact that everything is going around at that speed. In fact, actually on Earth, we're going around 1,000 miles an hour. It's just that we don't recognize it because everything's going around at the same speed. But on Jupiter, okay, so on Jupiter, can you take a picture from the surface of Jupiter? No, because there's no surface. It just gets denser and denser as far as we know, and then pretty soon there's a solid core of hydrogen, metallic hydrogen, down there creating a big magnetic field, much more intense than on the Earth. Tagline, that's a good point. In other words, and then also they're speculating because those colorful looking clouds have a little bit of organic in it. Mostly it's non-organic, but they got a little bit of organics. And so as they fall in toward the surface down toward the center of Jupiter, they ammonia and methane is what I understand. And then what they speculate is some of the organics that fall down toward the middle of Jupiter get crushed so much that you've got this rain of diamonds. Isn't that an interesting thing to picture? In other words, they get crushed into diamonds in this little sprinkle of tiny diamonds, or how many eyes are a crushing item? I don't know. I wouldn't find out. Diamonds in the sky. Da 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 da. Let's see. Let's see. Lucy in the sky with diamonds. Da da da. Don't. Yeah, Lucy in the sky with diamonds. Okay. Yeah. Okay. So anyway, exactly. Yeah, is what I understand. Okay. So anyway, but we can kind of speculate what it might look like on a moon of Jupiter. So here's a picture of somebody's imagination of what a moon might look like around Jupiter. Oh, yeah, they denied it, but they might not today. Okay, but anyway, here again, you got your white sun out there, which is a lot smaller than Mercury. It's kind of cold out that way, but this might be what it looks like on a moon of Jupiter, looking at the big planet itself. Okay, does Saturn or Titan have seasons? Anybody happen to know before you read this? In this case, what I read was yes. In other words, you'd think no, the same way as Jupiter, but, oh, really? I didn't know that. Jupiter spacecraft mission, that's cool. First of all, it has an axial tilt, and so it creates seasons. The seasons happen to be 7.5 years, Earth years long. And then you can actually see this North Polar Vortex. Well, actually, my understanding, Illing, and we'll talk about that in a second here, and I'm watching my time because I've got a couple planets left, is it's not made totally of ice, except that ice is basically as hard as a rock, literally. And there's ice rocks on Titan and stuff. And so it's got a lot of ice, but there's also methane seas. In other words, not just methane, but hydrocarbon seas, hydrocarbon rain, what looks like glaciers. I'll show you a picture in a second. It's really cool. It's the only other planet where we have seen, yeah, there you go. It's the only other planet, or methane and other hydrocarbons. So it's the only other planet that we've seen that has the same sorts of features that the Earth does. And so Saturn, it has a polar vortex thing that becomes prominent in the spring and then recedes in the autumn, and then high altitude carbons, and then Titan is really cool. Let me show you a picture of Titan. Anybody follow the Huygens space probe? I'm trying to remember the name of the Huygens, this one here. These are actual, not the one in the upper left. The one in the upper left is a fictitious it's a imagined picture of what it might look like on Titan. But on the bottom left are the actual, there's lakes and seas that they've actually measured with like not a, let's see, what is it, 30, like 50 meters deep, that sort of thing. Methane seas, and you look at those mountains. That looks like glaciers, and then you've got ice rocks and the whole bit like that. Most cool. Yeah, Tag, that would be, in other words, lighting a match would be Cassini. Yes. Cassini and the Huygens space program. That was marvelous. I just loved it. Because the atmosphere is actually, it's the only moon that has a thick atmosphere like that. And so they were able to use parachutes like they do on Mars, and they can't do on the moon, which makes it more difficult to land on the moon. It was Titanic. Okay, I didn't even get that. Thank you. Okay, how about Uranus and Neptune? Well, one of the planets, which one is it? Uranus is on its side. In other words, it's just a little over 90 degrees. Something must have whacked it hard back in the early part of the solar system, because essentially the poles are facing you. So what happens is one hemisphere has a long, relatively hot summer. The other has a long winter. We're talking about 80 in 21 Earth years each because of its 84-year orbit. And so sort of yeah. Okay, and then Neptune experiences seasons of 41 years each because it has an axial tilt similar to Earth's and an orbit of 165 years. And Hubble has actually seen seasonal spots and rings basically change during these seasons because of which of parts of it that are faced toward the sun, parts of it that are faced away, even though we know that it doesn't get a lot of solar radiation. And I'm usually pretty good about making this go all the way to 1 hour. But this may be my last slide. Let me see. Oh, no. Okay, almost. There's a very imaginative picture of, very imaginative picture of Neptune with, there's a spot there, just like on Jupiter. And this is one of its moons. Yes, exactly, Amalak. In other words, the same thing. The Earth is presumed to have the tilt it has because a object the size of Mars whacked it back in the early part of the solar system, and then created the material together, then created the moon. And also the core of that object then sunk towards the Earth. Theia, exactly. That's the name. Theia. And it sunk down toward the center of the Earth, and so we have a larger iron core than we normally have. Rings, absolutely. They're less famous than Saturn, but they've seen differences in the rings depending on whether it's summer or winter on there. And I think I'm finishing up. Yeah, exactly. Everybody has rings. Now, there's actually, you can see them through star opposition. In other words, when the stars go behind the planets, you can see them. 13 known rings. That's interesting. Much darker, narrow. Okay, that's interesting. Okay, now, it's presumed that when this Theia hit Earth, rings of power. Okay. I never did watch the second one of that one. Okay, so anyway, let's see. It's presumed that if you were back at the early part of the solar system, you would have seen essentially rings around Earth, because when Theia hit, all that material would have been whacked off the outer part of Earth as they both kind of melted, and then you'd see big non-stable rings that all kind of got together and created the moon. And then at one time, there was also another object other than the moon, which then they're speculating hit the moon, and that may be the reasoning why you have the Maria and stuff on one side versus the other. If anyone knows that sort of thing. Okay. And I think this is my last. Well, okay, similar what happened to Theia. Okay, so Theia was a Mars-sized object, which means pretty darn large. And it came close to Earth. Everything was kind of flying around back then differently. Exactly. And so it hit the Earth, but it hit it at a glancing blow. It didn't hit it straight on. Otherwise, they both would have just kind of got one kaboom, and you'd have stuff all over the orbit that would coalesce. But it hit it at a glancing blow. And it was enough energy transmitted to, it kind of bounced. But in other words, it hit it enough, not head on, but enough that it melted both planets, well, Theia and the Earth, proto-Earth, and a lot of the, yeah, exactly, and exactly. In other words, it left a lot of the heavy material to sink to the core of the Earth, and then the outer material, which they found out when they went to the moon and got moon rocks, is a lot like the outer part of the Earth. In fact, so much as far as isotopes and stuff, that's where the theory came up. It's like, okay, this is too much of a coincidence that it's like that. So then all that stuff collected and created a moon, which then has been receding from the Earth ever since. It's still going away from the Earth at a centimeter per year. And back in the dinosaur days, actually, the Earth, and also because, yeah, so the day back in the dinosaur days was actually only 23 hours long instead of 24 hours long. Yeah, exactly. Very, very, very hot, molten. Took a while to cool down. It took a while. In fact, it took quite a while for it to be cool enough for all of that humidity in the atmosphere to rain to the Earth and create the oceans, which the oceans they also think came from comet ice and that sort of stuff. Sis, I actually read that the Earth's day was 9 hours at one point, back when you're talking about the time when it had enough rotational energy. In other words, from the impact and stuff. You could take a look it up, but it's been getting longer. Yeah, ever since. Okay, so I think I am on time. Yay! Okay, so that's my presentation for today. Any comments, questions? I love the comments, by the way. I always like that because I like angular momentum. There you go. Transferred to the moon to move its orbit. Excellent. Okay. Thank you. Yeah. Yeah, I thought it was interesting, but like I said, it all starts from kind of a spark. It's like all good science. It starts from a question going, I wonder if there's seasons on other planets, and then you have to do some research, put it all together, make sure you got definitions, all that stuff, and then it becomes interesting. And I learned something. I get to share it. So I love it. Oh. My smart whatever is thinking I'm talking to. Well, there you go, Oppen. See, that's the other thing is most people probably have not. So I'm going, well, that's interesting. And partly it's because I was thinking of Mars with the sandstorms and the poles. And so it's like, okay, let's see. Okay. And so we're now an hour into this, so I'm going to quit. You're welcome to hang around and talk and whatever. And I appreciate everybody coming today. Thank you.